Okay, let's continue in chapter 18. This is part 2. The last topic that we covered in chapter 18, right, for video 1, was that the translational energy for monatomic gas is equals to 3/2, right, number of particles, right, boson constants times the absolute temperature. Now, let's see when we work with this translational energy. Actually, it's the average, remember, so it's equals to 1/2 mass times the average square, correct, of the velocity. So that equals to 3/2 nkvt, correct. Now let's solve for this velocity, average velocity. So do we have this average square velocity is equals to 3n over mkvt, correct. Now let's go to numbers of moles. Remember, numbers of moles is equals to numbers of the particles over Avogadro's number, correct. Also, this is equals to mass divided by molar mass, correct. Now from here, let's solve for n. So n is equals to mass over molar mass times Avogadro's number. Let's substitute this value right here, and what do we have? So this is equals to 3 times n, but n is equals to this mass over this molar mass, correct, times Avogadro's number times Boltzmann constant times the absolute temperature. But remember, this is a constant too, so this is equals to 3. Also, we have m's right here. Look, m cancel with this m, and this is equals to 3 r t, correct. 3 r t is gonna be this average square velocity, correct. So from here we have then that this average square velocity is equal to 3 rt. Great. Now let's look for the velocity. Let's take the square root, right? When we take the square root of this quantity, of this average, we create the root mean square speed, right? The root mean square speed is equal then to define as the square root of the average square, right? Perfect. So this is equals to, again, we took the square root of the square root right here, so it's equals to the square root of 3 rt. Great. So it's a very important quantity in physics, right? The root mean square, the root mean square speed is equals then to what? To 3 square root of 3 rt. Perfect. Let's prove this one later. Okay, this is found using distribution of the speed according to Maxwell-Boltzmann theory. Okay, great. Now let's go to the next topic, which is heat capacities. Okay, heat capacities. Let's do it. Remember the symbol for heat capacity, especially more heat capacity, right? Molar, right? Heat capacity. Especially, let's pay attention on at constant volume. At constant volume. Okay, it's found that it's different when we add heat, right, to a sample. If the system is at constant volume or at constant pressure, right? The change in temperature is different. Okay, I'm gonna see you later. Great. Now let's go to this quantity again. One more time. Remember, we found that the translational energy is equals to 3/2, correct? 3/2 nRT, correct? Perfect. Now what happens when the temperature changes? Okay, by dt, okay? There's more changes, so we have also more changes in the kinetic energy, correct? So do we have this change in the translational energy is equals to 3/2 nRT. Okay, now, but we know how we can create this change in temperature. Well, when we add heat, right? We have a sample of gas, we add some heat, and we add heat at constant volume, right? Constant volume, the temperature increases, correct? But heat is energy. Heat is energy, or energy transfer, or energy in transition. So that energy must be related with translational energy, right? Heat, temperature is no energy, right? But this one is energy, kinetic energy, right? So what do we have? Well, when we use the formula for heat capacity, in this case molar heat capacity, we found before, this is equals to numbers of moles, heat capacity constant volume, correct, times dt. At the beginning the formula was like this, right? Was like that, correct? But now because we are going specifically to constant volume, well, we represent that, excuse me, using this notation, correct? Now because energy are related, so means the heat added to the systems actually equals to the kinetic energy, which is converted completely to kinetic energy, translational kinetic energy. So what do we have? Well, we have that this translational amount equals to this amount of heat. Then when we compare these two equations, what do we have? And right, more specific, molar heat capacity. Molar heat capacity, dt is equals to 3/2, right, and r dt. From here, we conclude that the molar heat capacity at constant volume, correct, is equals to 3/2 r. Correct. Later we have one more constant pressure, and that's for next chapter. Okay, perfect. Great. Now, let's see what happens when, because we're dealing with energy, right here, energies, the heat is converted to energy. This is a special case when we have monatomic gases. What happens if we have a diatomic or polyatomic gases, correct? Well, it is found that this heat is converted not only into translational, but also into rotational, right, energy of the molecules, also into the vibrational energy of the molecules, correct? So let's see what happens then, what should be the total energy when we involve now a rotational motion and vibrational motion. Actually, this is for the next chapter that says that the internal energy is the sum, right, of all the energies, translational plus rotational plus vibrational energy. Okay, perfect. Let's see what happens then in this case when we have a diatomic gas with a rigid rotator, like this one. Okay, let's go to diatomic molecule, diatomic or gas, right? Correct. And imagine this is the situation we have. This is the diatomic gas, diatomic molecule, correct? And this is this rotator is rigid, is fixed, right? Rigid. Okay, rigid rotator. Perfect. So in this case, it can rotate in this direction and in this direction, correct? We have rotation, rotation. But it cannot not rotate on this direction, right? Parallel to this rod, right? Only on this way, right? Or in this way, correct? In this way or in this way. Perfect. So now let's see what happens. In this case, we have to define some concepts like degree of freedom. Let's define degree of freedom. Degree, correct, of freedom. Let's define it in this way. The degree of freedom of a molecule, is a way, correct, in which it can possess kinetic or potential energy. It can possess like this, possess, right, kinetic energy and potential energy. Correct. Now we have another statement that helps us to work with this analysis. It's gonna be the equipartition, right? Equipartition, right, of energy. Okay, it says that each degree of freedom, we're dealing with degree of freedom, right? Each degree of freedom has an average energy, right? Has an average energy, right, of 1/2 kT. Correct? Remember, when we're dealing with monatomic gas, we found that there is only translational energy, right? Translational is equals to 3/2, right? 3/2 with the eraser, 3/2. Correct. 3/2 kT. Okay, also we have this one. We have N, we have K. This is for K, kT. Perfect. So this equals then to look 3 times 1/2 kVt. This is the equipartition of energy, because when we're dealing with translational motion, right, monatomic ideal gas, we have only energy in X, Y, and Z, right? So we have X, Y, and Z, right? We have 3 times each, let's say, each component, X direction, Y direction, and Z direction, right, has 1/2 kT, because we have 3, so the torque is what? 2 times 1/2 kVt. Correct? Okay, that's the meaning for this analysis. Great. Now let's go to diatomic. In diatomic, we have to add, right, two more energy, right? Remember, in this case, we have rotational energy. Rotational energy equals to, remember, 1/2 modulo inertia omega squared. So what should be then the torque energy? The torque energy then, later this is called again internal energy, but on this chapter just is called energy. Okay, so it's equals to, again, we have translational, which is 3 times, right? 3 times 1/2 kVt, correct, plus for rotational, because this is rigid, right, it's fixed, we have only 2 energies for rotation. It's going to be 2 times 1/2 kVt, according to the equipartition energy. Correct? So what should be the total? The total is equals to 5/2, right, kVt. Correct? That should be, again, for diatomic gas. We have this quantity for the torque energy. This is happening actually, for example, if we have a diatomic molecule, let's say hydrogen. When hydrogen is used, right, when the temperature is not so high, right, this molecule behaves as only one particle, correct? But if the temperature increases, now rotation must be to take into account. If the temperature increases even more, now we have vibration to be taken into account. What happens in that case when we have vibration? This is only, again, for diatomic, when we have rigid, right, rotator. Later, again, what happens when we increase the temperature? Now, in this case, this is no more rigid. Now, it's gonna vibrate, right? So we have 2 more degree of freedom, right? 2 more degree of freedom, because we have kinetic and potential for the spring, right? Imagine that behaves as a spring, correct? For example, remember the, one more time, let's put it right here. So energy, total energy, correct? Total energy, total, we found 5/2, right, kVt. This is for this case. Now what happens when the temperature increases? Now it's no more rigid, right? And now this behaves as a spring, right? What happens when we have the spring? Where vibrate? What is the total energy of the spring? the total energy of the spring, right, is equals to, remember, kinetic plus potential. What is the kinetic? Kinetic, well, is 1/2 mv squared. What about potential? Potential energy for the spring, 1/2, right, kx squared. So we have two more energy according to degrees of freedom. We have 2 more degrees of freedom for energy. So what should be then the total energy for this diatomic molecule? Well, we have that the total energy when we involve now vibration, right, total is equals to 3 for translational, right, according to the equipartition energy, kVt, correct, plus what? Plus 2 for rotational, correct, 2 for rotational, 2 times 1/2 kVt plus 2, right, for vibrational. Remember, we have kinetic plus potential, okay, plus 2, 1/2 kVt. Perfect. What is the total? The total is gonna be 7/2, right, kVt. Correct. So again, we have another one right here. Total. Now we involve vibrational energy. Correct. Gonna be 7/2 kVt. This is 5/2, and so on. Got it? Okay, this is found in the experiment. Okay, this analysis, this result is found in the experiment, correct? And this is more or less the behavior in the experiment. Again, if we have, in this case, the atomic molecule of hydrogen. So this is what is happening. Okay, this is, let's say, 3/2, and then we have 5/2, and then we have 7/2. Correct? And this is the same thing, right? Also, we can represent this as the molar, right, specific heat. Correct? Correct. We just did it before using energy. Okay, we can represent this as more specific heat. Okay, more specific heat. Correct. This is energy. But what about the more specific heat that we found before? It's gonna be for, like in this case was 3/2. It's gonna be 5/2 RT for this case, right? When we compare this again to energy, the same thing as we did for monatomic ideal gas, right? It's gonna be 7/2 RT. Correct. This again are coming from energy, the same thing as this was coming for translational energy. Perfect. Okay, at the beginning, okay, we have has this value. Now this is temperature, right? Temperature increases, it gets this value, right? And then temperature increases again, right? It gets that value. Correct. Now from here to here we have a translational, right? Translational. From here to here we have rotational, and from here to here we have vibrational. Of course, it's 0 when temperature increases. Correct. We have to add more degrees of freedom. Correct. That increases the molar specific heat at the same time while we increase the internal energy in the same rate. Correct. Perfect. This is for gases. For solids, right, when we have monoatomic solid, for mono, this again is for hydrogen, okay, the molecule of hydrogen, okay. Now let's go to a monatomic solid. Right, when we have this crystal only with one atom, correct? So it's found that the molar specific heat is equals to 3R. Well, it's more than what we have ideal gas, more specific. heat or molar heat capacity. I was calling more specific here, molar heat capacity. Okay, perfect. Now let's go to the speed, right? Let's go to the molecular speed and let's use the Maxwell-Boltzmann distribution for these molecular speeds. Let's do it. Okay, molecular speed. Molecular speeds. Perfect. Okay, and this is according to Maxwell-Boltzmann distribution. Okay, Maxwell-Boltzmann, okay, distribution. Where is the eraser? Right here. Okay, Boltzmann. Okay, distribution. Okay, this is from statistics, right? This is the formulas. So kind of complicated formula, but let's try to do it. So we have that this change in number, right, of particles, molecules is equals to the numbers of molecules, correct, in function of velocity in that interval of velocities, correct. From here we have, right, that this equation, let's arrange in this way, it's gonna be equals to this function of velocity dv, and this is equals to, let me write it right here, we're gonna use it later. So we have that this change in the particles divided by the numbers of the total particles is equals to 4 over square root pi molar mass divided by 2RT to the 3/2 times V squared times E to the negative molar mass, right, V squared over 2RT dV. Correct? The meaning for this quantity is that this represents the fractional number of molecules, right, with a velocity in the range of dV, or this velocity, right? So this is a fraction of particles with velocities in the range of dV. There's the small right fraction. Okay, perfect. Now let's see what happens then when we're looking for let's say the root mean square speed using the distribution. Also, let's find the average speed, and also let's find the most probable speed. Okay, this is from the experiment. This is for nitrogen at 0 Celsius. It's found for nitrogen at 0 Celsius. Correct? That more or less this is the behavior. More or less like that. This is nitrogen right at 0 Celsius. So we have the maximum right here, maximum, and then so we have temperatures, correct? This is 400, this is 200, this is 600, right, and so on. This is 800. This is actually velocity, right? This is velocity, and this is velocity in meters per second. So we have this is the maximum. It's called the most probable speed. Later we have another one right here. This is the root mean square, right? Root mean square speed, and then we have one more in between, and this is the average speed, right? The average. Okay, let's try to calculate all of them. Let's just start with the most probable speed. So it's the maximum. When we're dealing with in calculus, right, and we have, right, a function, we have a curve, we have maximums and minimums. How do we have the maximum? Remember, we have the maximum when we take the derivative of the function and we equals that derivative to 0, correct? So what do we have then? What is the function? It's this function, right? Let's derive this because we're dealing with speed. Let's derive this with respect to speed, right? Let's derive this quantity and let's make it equals to 0, correct? It's gonna be 4 square root pi molar mass, right? 2RT to the 3/2 v squared e to that quantity must be equals to 0, correct? So you can see this is constant, so we send it over there, correct? And actually we are looking only for, or we divide by this quantity and it becomes 1, correct? So we have only the derivative with respect to the speed of v squared e to this quantity, correct, must be equals to 0, right? And when we do it, what do we have? We have 2v times e to this quantity, correct, plus what? Plus v squared, correct, times the derivative of this quantity, right? What is the derivative? It's gonna be e to the negative of this quantity minus, actually it's gonna be minus what? The derivative of this quantity is gonna be what? Minus 2 and v, correct, divided by 2RT times e to this quantity must equals to 0, correct? Perfect. We divide by this exponential right here. And also look, we divide by velocity. Oh, I forgot something right here. Oh, that's fine, it's velocity right here, correct? And then what do we have? We have that this is what? This becomes 2 minus, we divide it by v, right? We have only v squared, correct? v squared divided by this, divided by, okay, these two is cancelled. We have m on the top, right? M and RT. This is M, the big M, right? The big M, okay, big M. The big M, okay, perfect. Equals to what? Equals to 0, correct? From here, we solve for, no, this 2 is cancelled, right? 2 is cancelled. So what do we have? We have that V, right, which is called the most probable speed. More probable speed is equals to the square root of what? 2RT over M, correct? So it's gonna be the most probable speed. Most probable speed is equals to square root 2RT over molar mass. Perfect, that's the way how it's found that quantity. Now let's go to the average. Okay, let's go to the average. The average velocity using this formula right here, this complicated formula, right, is found in this way. Have a formula to find average. Okay, the average velocity is equals to the square root of v dn, right, over n. Perfect. But this one equals to, again to 4 square root pi m over 2RT, correct, 3/2 times the integral from 0 to infinity of v cubed e to this right power dv. This is found from table, right? This is from table, this quantity, right, from table is found to be 1/2 2RT over molar mass, right, cubed. This is from tables, correct? Now when we multiply this times this quantity right here, it's found that the average is equals to, or the average speed, right, the average speed is equals to square root of 8RT, correct, over pi molar mass. Okay, finally let's go to the root mean square. Perfect. Now let's find the average square, correct, and this is equals to, it's the same as this one, right, it's the same as this one, The difference is this power right here. Okay, the average, let me use the same. Okay, the average square. Okay, now, right, the average square, correct, is equals to this square right here, and this is equals to this to the fourth power, correct? And the same thing as before, we have that the integral is coming from tables, correct? From tables, this is equals to the whole thing. Right here we have the whole thing that is equals to 3 RT over M, which is going to be the same thing as that one that we found without these calculations. Okay, so the same thing, we found that when we take the square root and the square root right here, we create the same equation as this one, right? The root square speed is equals to the square root 3 RT, correct? 3 RT, what happened? Is this the same or not? What is happening right here? What is happening right here is divided by, oh, it's divided by molar mass. I can't believe it. So it's a different one. What I was thinking about this, is it correct? Did I miss something on this, the first equation, on the equation that we did before? Yeah, I missed that one. No wonder. Okay, molar mass. Okay, molar mass. I can't believe it. Sometimes that happens. I put it right here and probably right here. I forgot. Okay. Perfect. So you can see we get the same answer, right? The same answer as for the analysis when we have translational energy, and when we use, right, the mass or Boltzmann distribution of the speeds, molecular speeds. Got it? Perfect. Great. And with this, we finish chapter 18. Remember, this is a quick review, a quick analysis of the chapter. We have taken the most important point, not all the points, because they're gonna be so tedious to explain right in detail all the points per that is coming in each chapter. So again, this is a very important subject, correct? And with this, we finish this chapter. Okay, see you in the next one.